Hello and welcome to Mystery Science. I'm going to do something slightly different today and veer away from the physics, which is my specialism, and have a go at describing this chemical calculations, the infamous Edexcel CC9. Now, I've done these lessons as live lessons for my Year 10 students recently, and some of them have asked if I could record them for the YouTube channel so that they could go back and pause bits and replay bits so that they could get a better grasp of what's going on. And so here we go. Here is my attempt at explaining this. Now, this module, CC9, is really important for being able to calculate chemical reactions, the amounts that you are going to get out of a chemical reaction, the amount of reactants that you need, and the amount of product that you're going to get. Now, some students find this really complicated, and I have to admit to you that just this morning, as I was thinking about lesson 3, which is about moles, something suddenly occurred to me that had not occurred to me in my 20 plus years of knowing about this stuff. And without being taught anything or told anything extra this morning, it suddenly hit me what's going on. And so I'm hopefully going to be able to share that with you in a future video. But that's kind of how this module works. And I'm sat here now thinking, well, this is just blindingly obvious. And this is where this module is really difficult to teach, because once you've got the maths correct, it's very, very easy. The trouble is trying to work out what you're doing. Many students want to know why they're learning something. So part of teacher training is not is showing teachers how not to just give the facts, but also to explain why we're doing it. And this is difficult because it's hard to explain what we're doing here without actually doing it first. And when you try to do it that way round, trying to explain what we're doing, it gets even more complicated and it starts to mess with your mind a little bit. So I always start and I always tell my students that we're going to go through this. I'm going to give you some simple calculations and some facts. You just need to suspend disbelief for a while and try and get to grips with this first part, which is the easy maths. Okay, I promise you the first part of this is dead simple, and once you have it, it's there, it's simple, and you will think, well, why was this hard? But the trouble is, you might also be thinking, well, why am I doing this? And I promise I will get to that, and I will tell you why we're doing it. Okay, so here is the way we're going to break this down. We're going to start with talking about the number of atoms of an element in a chemical formula. Okay, it's going to be that simple. H2O, there are 3 atoms in the formula for H2O. Each water molecule has 3 atoms in it. 2 hydrogens, 1 oxygen. That's what H2O means. 2 hydrogens, H2, 1 oxygen. O, H2O. 3 atoms. 2 hydrogens, 1 oxygen. There are 2 elements there, hydrogen and oxygen. Okay? This hopefully should be fairly familiar concepts. Then we're going to calculate the relative formula mass of a substance from the relative atomic masses. And I'll talk about that in just a second. And then we're going to look at the difference between molecular formula and empirical formula. And this is where it starts to get unwindy and a bit melty in the head. So that's where we have to suspend disbelief for a minute. Let's not think about why we need an empirical formula. I'm just going to show you, teach you how to work out the empirical formula. And then later on, I'll show you why it's useful. We're going to determine the empirical formula just from its molecular formula. And that, again, once you've got the maths, is one of those things that's blindingly simple once you have it. Until you have it, it seems really hard. But don't give up, persevere, because, as I say, once you've got it, it's relatively simple. Then, the hardest bit we're going to deduce the molecular formula from a substance from its empirical formula and its relative formula mass. And even though I say it's the hardest bit, actually there's a nice and simple procedure to follow which makes it easier. All right, let's have a very quick recap of what all of the information you can get from periodic table means. Now, I know that my little box here is covering that label, and that's fine actually because I want to change what that label says, so don't worry about it. When you look at the periodic table, sometimes you see a periodic table that just has one number for each atom, and that's its atomic number. Now, we know from previous work that the atomic number tells you how many protons there are in that atom. It also identifies the atom. If an element has 6 protons, its atomic number is 6 and it's always carbon. If you have 7 protons, it's not carbon anymore. If you've got 5 protons, again, it's not carbon. Okay? 5 it's boron, and for 7 it's nitrogen. In the periodic table, you get the elemental symbol, so your capital letter or your capital letter and a single little letter, and then some of them will tell you the name of the element as well. It's quite useful to know. But then you have this other number. Now, sometimes this number's at the top of the symbol and the smaller number's at the bottom, and sometimes it's the other way around. It's the larger number. The larger number is the atomic mass, the relative atomic mass. And we denote that with a capital A and a small r. I'll show you that in a minute. But this tells you the weight, the mass of the nucleus. Okay, so if each part of the nucleus, both protons and neutrons, are given a relative mass of 1. So if you have 6 protons and 6 neutrons, each with a relative mass of 1, the relative mass of the nucleus itself is 12, because it's got 6 protons and 6 neutrons. So it tells you how many nucleons there are, which is things that exist in the nucleus. It tells you the combined number of protons and neutrons. Okay. Now, mass of 1 is a relative number. It's not really 1 anything. We've just decided that it's 1. And this is part of the realization I had earlier, and I will describe it to you when we do moles later on. But that's the principal thing. So to do this, to do these calculations, you need to make sure your periodic table has both of these numbers. The atomic, also the relative atomic mass, is important. So make sure, and if you're using the periodic tables that we've given you, that's a copy of the periodic table that will happen on the back of your exam. That will always have the relative atomic mass and the atomic number. Now you'll also see that a lot of these are not whole numbers. Depending on the periodic table you're looking at, they will either give you something like 12.01 or it will be rounded pretty significantly. So on a standard GCSE table, carbon is normally denoted as 12, and it's only when you get to chlorine, things like that, where it's 35.5. And that is because of isotopes. And if isotopes confuses you and you don't know why there isn't a whole number for the mass number, then have a look at my video on isotopes. That you'll find that in the CP6 section, where I describe isotopes there, or talk to your physics teacher about isotopes. Okay, so we need to define 2 different terms. First is the relative atomic mass, and that's the thing that I've just told you about. It is the average relative mass for an element. Okay, remember that electrons, the mass of an electron is completely irrelevant to all things. So it's only the mass of the nucleus that really matters. So we denote this with a capital A and a small r for relative atomic mass. So we know the masses for all of the atoms. So this extra term then, relative molecular mass, shouldn't really surprise you to know that that's the average relative mass of the atoms in a molecule. So you add all of the masses of each atom in a molecule up, and you'll get the mass of the molecule. Okay, let's have a look at an example. Water, H2O. Now, we've said before, H2O, there are 3 atoms here. So I just did that, but 3 atoms here, 2 hydrogens and 1 oxygen. Now, the relative atomic mass for hydrogen is 1. The relative atomic mass for oxygen is 16. But there are 2 hydrogens here, so we have to add 2 hydrogens together. And so the relative molecular mass is 1 plus 1 for both the hydrogens, plus 16 for the oxygen, which gives you 18. Water has a relative molecular mass of 18, and that is simply the all of the masses of all the elements added up together to make the mass of one molecule. Right, given that information then, here are 8 different molecules. I would like you, using a periodic table, to calculate the relative formula mass or the molecular mass for each of these, please. Let's have a look at carbon dioxide to start with. The relative atomic mass of carbon is 12, oxygen is 16, so if we add all of those together, we have 12 plus 2 times 16, which is 44. So the relative atomic mass of carbon dioxide is 44. Pause the video and have a go at the others. Right, welcome back. So potassium nitrate, then you've got potassium, which is 39, nitrogen's 14. You have 3 oxygens here, so O3. So it's 3 times 16 plus the other 2. So that gives you a molecular mass of 101. Calcium chloride, you have calcium, which is 40. Relative atomic mass of calcium is 40. Relative atomic mass of chlorine is 35.5. Just multiply that by 2. Add all of that up together, you end up with 111. Aluminium oxide, we have 2 aluminiums here and 3 oxygens. So 2 times 27, 3 times 16, which gives you 102. At this point, if you're getting the same answers as me, great, we'll carry on. But if you are finding that the answers are not what you're getting, then pause again, go back and see if you can work out how to get these numbers and then try again. Okay, so carrying on then. H2SO4, sulfuric acid, 2 hydrogens, 1 sulfur, and 4 oxygens. So relative atomic mass of hydrogen is 1, relative atomic mass of sulfur is 32, relative atomic mass of oxygen is 4. So we add all of that up, and that gives us 98. C6H12O6, our old friend glucose, that has a relative molecular mass of 180. Potassium manganate has a mass of 158. And barium hydroxide, be careful here, note that the hydroxide group are in brackets, and there's 2 of them, so there are 2 hydroxides here. So each hydroxide group is 16 plus 1 oxygen, 1 hydrogen. Multiply that by 2 and add 137 for barium, and that gives you a molecular mass of 171. Okay, we're going to move on to empirical formula. This is a molecule of glucose. It has 6 carbons, 12 hydrogens, and 6 oxygens, all in one pretty little molecule. Now, this is where I'm going to just show you the maths and how to work out the empirical formula before I tell you what it is. Because if I start trying to tell you what it is, you're going to get a little bit confused and try and work out, why do I want to do that? So just follow with me, and hopefully you'll see that actually if you suspend everything else, just this maths here, it's quite easy. So empirical formula, I've got here 6 carbons, 12 hydrogens, 6 oxygens. What I'm trying to do is I'm trying to make the simplest ratio of elements. See, as soon as I start trying to describe stuff, it starts getting a little funky. But here we go, just with the maths then. All I'm going to do is I'm going to try and find the highest common factor. See your maths teacher if you don't know how to do this, but here's a brief explanation. So I've got 6 carbons, 12 hydrogens, and 6 oxygens. To find the highest common factor, one way of doing it is to just go through all of the factors and see if it's the biggest one. Okay, so if you ask your maths teacher, I'm pretty sure they will tell you that there are easier ways than this to find the highest common factor, but here's the way I would do it. C6H12 6. I can divide all of those numbers, 6, 12 and 6 by 1. Okay, and I would end up with 6, 12 and 6. That's not very helpful. But I can also divide them all by 2, and I would end up with 3, 6 and 3. Okay, good. But if I can divide them by 2, and I get 3, 6 and 3, I can also divide them by 3, right? So I'll end up with 2, 4 and 2. So that's good. But I can also divide them by 6. So if I divide them by 6, then I end up with 1, 2 and 1. So that's the highest common factor. I can't divide anything else by that. So that's the best I can do. 6 is the highest common factor. So my simplest ratio for this molecule, my empirical formula is CH2O. Okay, because if I multiply all of those by 6, we ignore 1 because we just don't write it down. If I multiplied all of those numbers by 6, if I multiply 1 by 6, I get 6. Multiply 2 by 6, I get 12. And if I multiply 1 by 6, I get 6. Okay? So the simplest ratio of all of the atoms is CH2O. What does this mean? Well, this means that in my glucose molecule, C6H12O6, for every one carbon atom, I have one oxygen atom and 2 hydrogen atoms. Okay? And that's what the empirical formula is. I'm just basically saying, well, if I've got only one bit of this, how much of it have I got that I can repeat and build up? So let's look at the two different definitions for these formula. A molecular formula is a bit like a recipe. It's the number of atoms and which type make up a substance. So for example, for glucose, it tells you need 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. If you don't have those, you cannot make glucose. Whereas the empirical formula is the simplest ratio of atoms or ions of each element in a substance. And it's basically saying, right, well, what's the simplest form I can make this? It doesn't matter how many I need to make the molecule. I just want to know, well, for every carbon atom I have, how many hydrogen atoms do I need and how many oxygen atoms do I need? And that's what this empirical formula is. It's the simplest ratio of atoms of each element in a substance. So for example, C6H12O6, we've just done this. If I break that down and calculate the empirical formula and find the highest common factor, I end up with CH2O. Now, let me show you this though. This is C9H18O9. If you look at that, you might think, well, that's going to be a bit tricky, and I'm going to have to do more common factors. And yes, you're right, you are. You can now do 9 as a common factor. The first thing I look for when I'm trying to do the empirical formula is I look at the biggest number and I look at the smallest number. I say, well, how can I get that into that? And so if I can divide the biggest number by the smallest number, I've immediately got that ratio. So C9H18O9, if I divide all of those by 9, I've again got C, because 9 divided by 9 is 1, H2, because 18 divided by 9 is 2, and O1, because 9 divided by 9 is 1. So again, I end up with CH2O. So the empirical formula doesn't tell you anything about the molecule, because these two molecules have exactly the same empirical formula. I can say that in both of these molecules, for every carbon atom I have 2 hydrogen atoms and 1 oxygen atom. So even if I had C20, I know that if I had C20, I would need 2 hydrogen atoms for every carbon atom. So C20H40, and then the same number of oxygen atoms. So it would be C20H40O20. Okay? That would have exactly the same empirical formula as these two molecules. The molecular formula is completely different. They're 3 completely different molecules, but the empirical formula is the same. It's the simplest ratio that I can get to. Okay? Okay, so here are 9 examples to try. Let's have a look at the first one together, and then you can pause the video and go for the others. C2H6. Well, I can divide both 2 and 6 by 1. That's not really very helpful. I can divide 2 by 2 to get 1, and I can divide 6 by 2 to get 3. And I can't go any higher than that. So my empirical formula is CH3. Before you go on and have a go at these, remember that some of these may not be able to be simplified. It might just be the lowest that it can be. It might be already in its simplest ratio. So bear that in mind. Pause the video and have a go at these. All right, welcome back. Let's have a look at number 2 then, N2H4. I can divide both of those numbers by 2 and end up with NH2. For every nitrogen I have 2 hydrogens to go with it. Number 3, C6H6. I could list all the common factors in that, but hopefully this one should be pretty obvious. For every carbon you have 1 hydrogen, so it's just CH. C5H10. If you divide 10 by 5, you end up with 2, and you can see that for every carbon you need 2 hydrogens, and so you end up with CH2. But what about question 5? Well, if you look at this, you can't go any simpler than C3H8, because both have a common factor of 1, everything does, but if you divide 3 by 2, you end up with 1.5, and you cannot have a decimal number. They have to be whole numbers. But if you divide 3 by 3, you end up with 1, but you can't divide 8 by 3. Therefore, it's C3H8. And question 6 is fairly similar. You can try and work out all the common factors, but the only common factor here is 1. You can't break it down anymore, so you end up with C5H12. And on to number 7 then, C2H4O2. Hopefully, by now you can see that this is a nice simple variant of our old friend CH2O. And then we've got glucose, which again is CH2O, as we've already worked through before. And then finally we have C2O2H4. And you can see that 2 is a common factor here, so you end up with COH2. Right, Mr. E, fantastic. I've got that. I can work out empirical formulas. Woohoo! Why am I doing this? What? Well, this does have practical applications. Now, if you can work out the simplest ratio for every carbon, I need 2 hydrogens and 1 oxygen, you can now start to work out the ratio of reactants that you need for these molecules. And once you know that, then you can start to work out how much of things you need to make a specific amount of a product. Now, remember that chemistry goes beyond just what we learn at school. Some of these are industrial processes. Some of these things are things needed for life and industry. So they have important practical applications. So businesses don't want to just willy-nilly throw in a bunch of carbon, some hydrogen and some oxygen and hope it mixes together to make something useful. They want to know precisely what they're putting in and precisely what they're getting out, so that their profit margins are as tight as they can get them. There's no point wasting money just throwing in chemicals higgledy-piggledy and hoping you get something out in return. I mean, by God, if you tried to make this or do the same thing for a cake and just went, I'm going to throw in 3 eggs, I don't know, a knob of butter and 12 tons of cream, you're not going to make a cake. You're going to make, well, you're just going to have a bunch of cream with a little bit of tiny sponge in the middle. So this is important. We need to know the correct ratios for things. But don't worry, I'm going to show you a nice easy way of calculating these. So if you know the masses of the elements in a sample of a compound, you can calculate the formula of the compound. So if I gave you a sample of a compound and you knew that 1.2 grams of that compound was carbon, 3.2 grams of it was oxygen, what is its formula? Well, let's calculate it and find out. Okay, so where do we start with this problem? Well, the first thing we do is we get matter. Grrr. And we're going to use this table. Matter stands for M, masses, A, relative atomic mass, D, divide, and R, ratio. So the first thing we do is write down the masses that we were given. So we were told we had 1.2 grams of carbon and 3.2 grams of oxygen. So we just write those down in the table. Then we use the periodic table and look up the relative atomic masses of carbon and oxygen. Carbon is 12 and oxygen is 16. Now what we do is we divide the mass, so the top number, divided by the relative atomic mass, and that's the second number, and we end up with this. So we've got 1.2 divided by 12, and then 3.2 divided by 16. 1.2 divided by 12 gives me 0.1. And 3.2 divided by 16 gives me 0.2. Now, the next thing I need to do is divide by the smallest number of those. 1.2 divided by 12 gives me 0.1. That's the smallest number. So 0.1 divided by 0.1, that gives me 1. And then 3.2 divided by 16 gives me 0.2. So if I divide that by 0.1, I'm going to end up with an answer of 2. So that's my ratio. I've now got 1 to 2. For every 1 carbon, I have 2 oxygens. So for 1 carbon, I have 2 oxygens. So I've worked out that actually I have carbon dioxide here. For every carbon, I've got 2 oxygens. And that is all that we're trying to do. Now then, if you're feeling brave, here is a lovely extension question for you. A farmer is trying to find how much fertilizer she needs to add to a field. She knows that the field needs 100 kilograms of nitrogen, and she's just bought some 10 kilogram bags of ammonium sulfate fertilizer. That's got nitrogen in. Look, NH4, 2, SO4. So the first thing you have to do is work out how much nitrogen there is in each bag of fertilizer, because you can't just get nitrogen and scatter that on your field. It doesn't work like that. So you have to have it that's or in this fertilizer. So the first thing you do is find the relative molecular mass of the ammonium sulfate. So things that are tricky here, remember the NH4, that's in a bracket, and there are 2 of those. So you've got 2 nitrogens there and 8 hydrogens. Once you've done that, calculate the percentage by mass of nitrogen in ammonium sulfate. So work out, to go through the matter process, how much of the nitrogen is in this bag. Once you've got that, once you've got how much of the ammonium sulfate is nitrogen, then you can work out how much of that is in the 10 kilogram bag of ammonium sulfate. And then you know you need 100 kilograms of nitrogen, so how many bags of fertilizer will she need? Remember that if she's got a 10 kilogram bag of ammonium sulfate, if that was pure nitrogen and that was all she needed, she would need 10 bags of that. She's got 10 kilograms, she needs 100 kilograms of nitrogen. So your answer has to be bigger than 10 kilograms, because not all of that bag of ammonium sulfate is nitrogen. Okay, you need to work out how much of it is. Right, I'm going to leave you with that. I will give you the answer in the next video. What I'd want you to do, please, is have a go at that and stay safe, and I'll see you soon.